All right, in this next type of density, we have a radial density function. So if a quantity only depends, if the density of something only depends on how far away something is from the center, so an example of something that varies like that would be population when you think of it with respect to the distance from an urban center or some sort of city. So you can sort of, roughly speaking, model a population's density based on how far away you are from a city. So in Philadelphia, you could think about how far away are you from Philadelphia, and then that density for the population should decrease the further away from the city that you are. Okay. So that's very different than a linear density. A linear density just tells us in a line. But here, this radial density, you might think it's still in a line, but the total quantity is figured out a little bit differently. So for instance, let's consider this ring right here. So at the center, let's say we have something whose density does vary with respect to how far we are away from some sort of center or central point. So here. So in our object, let's say, has this distance r, this measurement of r. So if we wanted to figure out the total amount of this density, maybe it's a population density, so we want to figure out the total population, or maybe it is mass. And this would be a radial mass density, not a linear mass density. Okay. So what we can do here is, again, this idea is very common in Calc 2, and that is we are going to split up our region, our area, whatever we have. We're going to split it up into lots of smaller pieces. So we take a big problem and we convert it into lots of little problems. Okay? So again, we're going to use the same idea here that we are going to have let's say the number of rings n is very large, so let's think of it as approaching infinity, in which case the change in r, delta r, would get very, very, very close to zero, very, very small. So this distance here, the separation, the length here, delta r, is very small. So again, like the previous problems, although the density is different here than it is here, and of course everywhere in between. So although the densities are different at these two opposite ends of this highlighted band, because delta r, in theory, we're going to push the number of bands to infinity, so this distance here is very small. So although they are different, they are approximately the same. So what we can do, roughly speaking, is say that the density throughout this entire band is the same, because this distance should be very small. So the density at any point within this band, any point, we're going to say is the same density. So what we can do is imagine then taking this band and imagine cutting it. Let's say we cut it right here. And then we're going to unroll it. What this will form is a rectangle. Now, would it actually be a true rectangle? No, it wouldn't be. Try this yourself. Get a sheet of paper, draw yourself a circle, two circles, I should say, two concentric circles. Maybe use a compass so this distance is actually, the same as this distance here. So do that. And then go ahead, take a pair of scissors, and actually cut this out. You can't unroll it and have the paper lie flat nicely. You'd have to smush it down. So it's not going to be a perfect rectangle, but it is approximately the same area. And you could actually compute this. Okay? And again, this distance, this separation here, delta r, this is not a large thing. So what you would do with a sheet of paper, that would be a really big difference, delta r. But mathematically, we're going to send n to infinity, so this delta r will approach 0. So in essence, as delta r approaches 0, the difference between the area of this thing and the area of this rectangle is negligible. Okay, so we're going to unroll that and we'll have a long, very skinny rectangle. So in principle, this distance would be very long compared to this distance here. I just don't want to draw something crazy like that. Okay, so what would, well, we already know what this distance is. This is delta r. So that means this distance here is delta r. And then this distance here, we don't quite know, but we could figure it out. Essentially, since this delta r is very small, we can say that it is either the circumference of this circle, the larger one, or this circumference. Doesn't matter because delta r is very small, so r sub I minus 1 and r sub I are approximately equal to one another. So let's just say r sub I. So we can say it's the circumference of that circle, whose radius is r sub I. So this would be, the circumference is 2 pi times the radius. So r sub I. Okay, so if we go ahead and now, let's go ahead and write in the units here. This would be units of, let's say, meters or distance. This would be units of meters or distance. So the area of this strip, so the area would be 2 pi r I delta r. This would have units of meters squared. Okay, so notice here, what we want to do is figure out this density. So if our density, for instance, is given by the amount of that substance or that quantity, so people, if we're thinking about a population density, so some quantity divided by, notice that we have area squared. Or so not area squared, just area, excuse me, meters or kilometers squared, excuse me. So this is an area. So this is quantity per area. So our density here, let's say density as a function of r is the units, or has the units of the quantity, whether it's population or mass, per area. And this right here has units of an area. So if we go ahead and integrate from, let's say, 0 to capital R for this problem, our area, 2 pi r dr times our density function, rho of r. Then this has units of area times the quantity whose density we're working with divided by the area. So the areas cancel, and this would give us the total quantity, whatever that quantity is. Okay? And essentially that's what we have right here going on, approximately. And then if we do a limit as n goes to infinity, this is the definition of a Riemann sum of the definite integral, a limit of Riemann sums, and this is what we get. So unlike a linear density, for a linear density, let's compare and contrast this. So if we compare with a linear density, So if, let's say, rho of x is a linear density of some quantity, population, mass, electric charge, whatever, it's a density of some quantity, then the total quantity is the integral, let's say some bounds, a to b, of just the integral of your density function. However, for a radial density, you are going to integrate your density function, your radial density function, but you also have 2 pi times r. So it is a little bit different. So the important thing here are these extra features we get. Okay, so let's take a look at example 8. The density of certain species of animals can be modeled using a radial density function where r is the distance from a central source of water. If the radial density function is rho of r equals 52 times the quantity 1 plus r squared quantity to the negative 2, animals per kilometer squared, so animals per unit area, determine how many animals of such a species will live within 5 kilometers of the water source. So the water source is located at r equals 0. That's the central feature. Okay, so I'll say that let's say the total population, P, is the integral 2 pi from 0 to 5 kilometers of r times our density function. So 52, 1 plus r squared quantity to the negative 2 dr. Of course, 52 is a constant. I can pull that out and get 104 pi. And then not only that, I can do a u substitution on 1 plus r squared to get 2r dr. In fact, I won't multiply the 52 by 2 because we're going to take this 2 and this r dr to form our du. So we'll just bring the 52 out with the pi. Since the 2 is going to go away, it's going to be useful to us. So we'll change our bounds then, since this is a definite integral. So this would be 1 plus 0 squared, so u of 0 is 1. And u of 5 is 1 plus 5 squared, so 26. So this becomes the integral of 52 pi from 1 to 26 u to the negative 2 du, which is negative 52 pi over 1. So really, right, we're adding 1 to this exponent. So negative 1, we're going to divide by negative 1, which really is the same thing as just multiplying by negative 1. So we have that. And this would be u to the negative 1 between 1 and 26. And u to the negative 1 is really just 1 over u. So there we go. So negative 52 pi, we'll pull that out, and then we'll do our evaluation of the bounds within this set of brackets. So this would be 1 over 26 minus 1 over 1. We can get a common denominator here. We'll just multiply this by 26 over 26. So then we would have, let's see here, this would be negative 52 pi times the quantity, 1 minus 26, so negative 25 over 26. So this cancels out. So we have whatever 25 times pi times 52 is over 26. And it says a certain species of animals. So let's just say animals. They didn't say what species of animals. Okay. So because this is a this is a density function of something that can't be a whole number, right? Members of a population, they are whole numbers. So when we're doing this integral of a density, you can have a fraction or a decimal for the density. So really, it would be useful to actually figure out what this is. So if we do that, 25 times pi times 52, divide that by 26. This is, I'm going to go ahead and just do a little aside here. This is about 157.08. So if we round to the nearest whole number, this is about, let's say, round to nearest whole. I'll just say integer, a whole number. This is going to be 157 animals. Because when you give units of something that can't be anything other than a whole number, and then you put that in front of something that is certainly not a whole number, it just is a little bit weird. So it's better to then go ahead and just convert that into an answer that makes a little bit more sense conceptually.